Okay, here we go. So first of all, I have an announcement. The AMC 12 is coming your way. The AMC 12, the American Mathematics Competition.
Oh, I saw this. AMC.
And so you are all cordially invited to participate. It is a competition that has problems from algebra, geometry, probability, and we'll be holding it 6th and 7th periods on Wednesday, February
6th and 7th?
February 15th. Yay.
When?
Here. In room 209. There will be snacks.
Oh, yes, I
We
saw
didn't get snacks last
So
year.
if you are interested, I'll actually print out forms and you guys can sign up.
Who signed up? I don't remember.
Just making sure we don't have slots.
6th and 7th period.
Is that hard?
6th and 7th.
Yes, it's challenging.
就跟数学题一样，
Okay.
大家都玩一跟当玩一样玩。
这走着走着有，反正有一个提示。
Let me give you the big picture. For the month of February, we're going to be studying sequences and the related concept of series, which are sequences added together. And that's going to occupy our time. The reason that we're doing this is this. What series do for us are that they allow us to generally represent any well-behaved function. Currently, our theory of functions revolves around families of functions. We have polynomials, we have trigonometric functions, we have exponential functions, we have logarithmic functions, we have inverse trig functions, we have square roots, etc., etc. A lot of families. What series are going to do for us is to unify all those families by allowing us to represent any function that's well behaved as an infinite series that looks like an infinitely long polynomial. And having so represented, we can then do calculus like derivatives and integrals, etc., etc. So this is an extraordinarily important topic in analysis. In fact, I would venture to say that a large part of what analysis does is representing functions in terms of their, we're going to call them Taylor series. So that's our plan. And we're going to start at the very beginning with sequences. So here's our definition. By the way, fair warning, this is the month where students will sometimes really mess up by failing to recognize that because this is new material, they have to actually study. So studying is definitely required. Keeping up with your homework is definitely required in order for you to succeed during this time. So that's your fair warning. I put the word infinite sequence in infinite in parentheses because usually infinite sequences are just called sequences. So a sequence is a sub n. Is a function whose domain is natural or whole. And just a reminder, the natural numbers sometimes denoted z plus, meaning positive integers, is the set 1, 2, 3, etc. And the whole numbers, which are the non-negative integers, are the numbers 0, 1, 2, 3. In other words, what I'm saying is that a sequence is going to be a function whose domain is simply the integers 1, 2, 3, etc., or maybe 0, 1, 2, 3, etc. So, for example, clean up my handwriting there. Okay, and so, for example, consider the function a sub n equals 2n plus 1. This would be the set starting at n equals 1 of 3, 5, 7, etc. And notice that the dot 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 means this goes on to infinity. So you can see how the role that n is playing right here, we call n the index, but it is really the index right here, but it is really representing the elements in the domain. Yes?
Is that 2n?
Yes, 2n plus 1. Or, for example, bn equals 3 times 1 half to the n minus 1 would be starting at n equals 1. And plugging in the successive values of n, we would get 3, 3 halves, 3/4, 3/8, etc. Yes, sir?
What's the Z plus 4?
Z plus is the symbol for the natural numbers, the standard medicine. Yes.
How do you know whether to start at 0 or 1?
That's a great question. If there is no information, the default is the natural numbers, but sometimes it is convenient. For example, with the Fibonacci sequence, sometimes you'll see it labeled like this. And so if there is a need to start at 0, that will be explicitly stated.
Do we know that?
So the Fibonacci sequence, we're actually going to study that tomorrow. But while I'm here,
Wait, what is it called again?
these are the Fibonacci numbers. And tomorrow I'll explain the history, where they came from, so on and so forth. If you take a look at these numbers, it may not be obvious where they come from. But if you look at them kind of closely, or if you have some familiarity,
right?
right, that's right, you may notice that if I take and add up these two, I get that one.
Yep.
And if I add up these two, I get that one. And if I add up these two, I get that one. And
But it
these,
looks like elementary school.
good, great, excellent. So the Fibonacci sequence is there. Now, let's talk about forms for just a minute. Yes.
What's the first one?
Oh, where the first one come from? So in the Fibonacci sequence, you actually have 2 of them given to you as initial values. And then you go.
Oh, so you said the natural numbers are the default numbers.
The default domain. Whole numbers are also possible. And sometimes, rarely, you can have the whole integers, all of the integers as your domain. So you could have a sequence that starts at negative infinity and goes to positive infinity. Now, I want to talk about forms, because there are going to be 3 different forms that we can represent sequences in, and here are 2 of them. The third one we get tomorrow. The first form that we have is a closed form. And in the closed form, I actually give you a formula. And the closed form looks like this, where the braces are sometimes optional. So sometimes you'll see it with braces and sometimes not. closed form is in many cases the easiest to work with.
Sorry. I'm trying to.
Second, you can have enumerated form. Enumerated form enumerates as many elements as is needed so that you can figure out the pattern. The advantage of the enumerated form is that it's a little bit more concrete. The disadvantage of the enumerated form is that it leaves you to figuring out the pattern for yourself. So for example, here for the Fibonacci sequence, what I did was I just gave it an enumerated form, and you had to kind of know or figure out or guess the pattern. And the third form that we're going to talk about tomorrow is going to be a recursive form. But we'll get there.
Oh, do we need to know how to transform from the enumerated form to?
Great question. Yes, that makes a whole lot of sense that we might want to do that. Enumerating, if you're given closed form, it's pretty easy to start enumerating, right? I just plug in any 1, 2, 3. For going from enumerated form to closed form, we're going to need to pattern match. And so I'm going to show you the two most common patterns that show up, the arithmetic and geometric sequences. But so far, the only thing that I want you to observe is that this is the notation, like so, a sub n. Its domain is going to be the natural numbers or maybe the whole numbers. And our sequences can come to us in closed form or enumerated form. Those are the points so far. Now,
John.
let's consider two common patterns that show up in problem solving all over the place. Can I help you?
Oh yeah, I just want to see the. No. Sorry.
No, that's fine. Just want to make sure I wasn't missing something. And the first common pattern is an arithmetic sequence. I'm pretty sure
How to spell it?
I spelled that wrong.
A1A3妈个屁呀！
Nope, it's good. Arithmetic sequence. Okay.
哦，
高明
哎，这他妈不是拿一好吗？
An arithmetic sequence is defined so that its terms have a constant difference between them. If you've been in math club, you recognize arithmetic sequences because we've done a whole lot in class.
I remember that you used it.
No, I never. You see, it doesn't reach.
You have like the sequence.
I'll show you all probably.
And when I say the terms have a constant difference, what I mean is that if I take any term and I subtract the term right before it, I get the same number every time. So examples of arithmetic sequences would be things like 1, 3, 5, 7, 9, etc. And here you can observe that each of my terms goes up by 2. That's a constant difference D. And so I can take this now and I can write it in closed form by using the arithmetic sequence form right here and identifying that A1 is equal to 1, that is our first term, and D is equal to 2, so that in general, A sub n is equal to 1 plus n minus 1 times 2.
我没说话，说出这个样子。
And we could simplify this if we wanted to, but it's not necessary. Now, if you look really closely, you can see that the form for the arithmetic sequence greatly resembles a form that we had for functions of continuous variables. What family of functions does this look like?
Linear.
Yes, that's right. Arithmetic sequences are linear functions whose domain is the natural numbers. And if you take a look even more closely, you can recognize that the form for the arithmetic sequence is identical to the point-slope form for lines. We have a point, which is our first term, 1 comma a sub 1, and we have a slope, which is that
Oh, isn't that
constant,
tangent line?
which is that constant difference, right? Well, not necessarily tangent line, but
I mean,
any line, yeah. So that we have the constant difference d playing the role of slope, and a sub 1 playing the role of the point here and here. All right, so I'd like for all of you to find a formula for B sub n. And what do you have, Justin? Does that work? Okay. Now, what does he need to identify before he's ready to put that in? He needs to identify the constant difference d.
Yeah.
What is that constant difference d between minus 4?
Back to
Ah, there you go.
我因为列排球真的很差很差，这个意思。
And by the way, what Justin just did there made an arithmetic mistake. Happens all the time. Because you have extra terms, check yourself. Yep. There you go. And another issue. So that's arithmetic sequences. Arithmetic sequences I present to you because they show up a lot in problem solving. We're not going to use them a whole lot in this course. But the next pattern we're going to use a whole lot. Geometric sequences. A geometric sequence is defined as a sequence whose terms have a constant ratio sequence whose terms have a constant ratio between them. In other words, if I take Gn and I divide it by the previous term, I get a constant ratio R. And you can see that geometric sequences are really exponential functions whose domain is the natural numbers. So this would be an example of a geometric sequence, and we call this G sub n. And if I wanted to write this in closed form, then I would need to identify the first term, which is 4, and I would also need to observe the constant ratio, which here is 1/2. So to get from here to here, I go times 1/2. To get from here to here, I go times 1/2, 7. And so therefore, I can write my general term as 4 times 1/2 to the n minus 1. Notice the role of n minus 1 here. What that's doing is ensuring that for the first term, I will get the first term. Does that make sense? One of the common things that can happen with geometric series is that they can alternate in size. If you take a look at the series, it's very interesting because the sign alternates. And the reason that the sign alternates is that my ratio is actually a negative number. So that what I end up having is 5 times negative 3 to the n minus 1 as my closed form. Now, sometimes people will pull that negative 1 to the n minus 1 separately out so that it's really clear that we have an alternating sign. So this is an extremely common mathematical way to express the alternating sign factor right here. And if I need to start with a negative sign, then I would make this negative 1 to the n rather than negative 1 to the n minus 1.
Can I just write like negative 3 over?
Yes. I'm not trying to limit you, I'm trying to give you flexibility in the way that you write things, and also to let you know how other people might write it. So these are geometric series. Sequences. I'm going to do that sometimes. Try to catch me. I'm going to accidentally call them series. These are geometric sequences. And they are extremely commonly used in analysis. We're going to spend some time on these. Okay? Now, the most important thing that we can do with our sequences is to determine whether or not they converge or diverge.
Oh my God. 不是了，不是了，这个CT 有没有学过？这个要背的，这是公式。不是这个公式，是另外一个公式。
I'm going to give you two different equivalent definitions here. One of them is useful for most computational purposes. One of them is going to be useful if we have to do proofs. We're going to say that a sequence A sub n converges to L. And we're actually going to use this notation for it. We're going to say that A sub n goes to L. If the limit, as n goes to infinity, of A sub n is equal to L. So that's not so bad. Formally, we will say it like this. If for every epsilon greater than 0, there is an n greater than 0, such that the distance from an to L is less than epsilon when n is larger than n. This is our formal definition. We will use it sometimes. And the picture that we have is this. here comes my sequence. And my sequence is going to look like a number of disconnected dots because its domain is only the integers, right? The positive integers. And now here comes the line y equals L. Like so. Try to do that. And so what this formal definition is saying is that if I choose some epsilon around L, some neighborhood around L, like so, then I can find a large enough n. I can find a large enough n right here so that when n is bigger than n, all of these points will fit in the epsilon neighborhood. That's the picture that's going on with our convergence. And now, kind of obvious thing. If A sub n does not converge, for whatever reason, it diverges. It might diverge to infinity, or it might oscillate forever, or it might do something else.
Wait, you said,
要么是应用给你，要么
what is it?
Converge or diverge?
when
How depends on the p.
What p? How see if
P is the degree of the n.
you're working too hard. A sub n is what it is. Converges to what value?
Zero.
And how do you find out?
Because the bottom go to
Goes to infinity, then in the whole goes to.
Right. We simply take a limit. Notice that if my function as a continuous function of x converges, then the sequence that comes from it must converge as well. Let's make that a theorem. If the limit as x goes to infinity of f of x is L, then if A sub n consists of the points of f of n, then it goes to L as well. This first is talking about a continuous domain function. This is talking about a sequence whose domain is just function. But the converse is not true. This function, this sequence right here converges to 1. Why? Well, enumerate it to find out. If I enumerate it and generate my terms, plug in n equals 1, what do I get? 1 plus sine of pi. What's sine of pi? 0. N equals 2, 1 plus sine of 2 pi.
0. And it's natural.
Exactly, that's
That's
right.
why, so it's
So Bn is actually just a constant sequence, even though it has a fancy formula.
It's interesting because it's all about natural numbers. So
Yes.
it has less concept.
Right. Yes.
But can you explain what the derivative is?
Yes. So f of x is going to be a function on a continuous domain like so. A sub n equals f of n is going to be just the sequence that is formed when I take the domain to be the natural numbers. It's just gonna be these points right here. So if f of x has some horizontal asymptote, like so, then a sub n is going to have to follow that asymptote. And as a result, a sub n is going to converge. But the converse is not necessarily true, as you see here. This b sub n converges to 1, but the function 1 plus sine pi x oscillates back and forth between 0 and 2. On the other hand, we have divergent sequences. Here's one. If we consider the limit as n goes to infinity, it's fairly clear that Cn is going to diverge to infinity. And here's one. dn is equal to negative 1 to the n. If we start enumerating, you can see that dn is going to oscillate back and forth between negative 1 and 1, and it diverges. Does that make sense? What about this one? Converge or diverge? To what value? Nope. Prove it.
I was going to say have what's in the parentheses be represented by a positive number.
So if you do it like for inside 1 over n goes to infinity, then it will go to 0. Then it will be 1 to the infinity. Isn't it going to be 1?
1 to the infinity. What do you remember about 1 to the infinity? No. Something about L'Hopital, right. It was an indeterminate form. Oh, way back. And in order to, it's not a L'Hopital's eligible form either, because it's not 0 over 0, nor is it infinity over infinity. How should I handle that fact? Which is what?
Equals 1 over n and have 1 over n be the exponent.
Okay. So if I do that, then I get the limit as n goes to 0, which is another form for this. I usually use z for this. You guys have seen this before Christmas. So this is an important piece of math literacy that you guys should definitely know.
Oh, okay.
What is this?
This is something we need to use natural logs for.
Ah, we are going to need to use natural logs for. So let's let y equal 1 plus 1 over n to the n power. Go ahead, Josh.
Okay, so we would have natural log of y equals the natural log of the limit, right?
Well, natural log is the limit of y. If that's the way that you want to go with it. Okay. Keep going.
And then we can, interpose the limit of natural log.
Why?
I don't know why.
Because natural log is a continuous function.
So we get n, limit is n goes to infinity, n ln 1 plus 1 over n. That makes,
What's our form at this moment?
currently we have infinity times
Right.
Oh, goodness.
right, and that's,
Oh, is that the time that we turn it into
that's what it
low
tells
top?
us.
It's not.
It needs
does.
alpha to become.
Yes.
Yeah, that's what I'm saying, like, it's time to
Good.
transfer.
What two forms am I looking for that are L'Hopital's element? And zero, zero. So we're pretty close.
So have ln 1 plus 1 over n over 1 over n.
Okay, now what's wrong?
0 to 0.
And we're ready to go. Go ahead.
So we get 1 over 1 plus 1 over n times negative 1 over n squared
Uh-huh. Good.
over negative 1 over n squared.
Good.
And so the terms cancel. And this n goes to infinity, that is 1.
Is 1. Okay. Now, don't forget where we came from.
Right.
This is the natural log of our limit. And so we conclude, therefore, that the limit as n goes to infinity of y is equal to? Yes. And in fact, this is the definition of E.
That's what, when I first saw it, because E was determined as,
Yes.
yeah,
because
exactly.
This came about by continuously compounding at 100% interest rate. This is Euler's number E. And it is the best example of the fact that the form 1 to the infinity is indeterminate. It is a matter of math, cultural literacy to know this limit, and it shows up on the AP exam frequently.
Cool. Impressive.
Impressive.
Yeah. Impressive. Okay.
The label was a slap.
What? Wait. Impressive?
It's wordplay.
Yeah.
Oh,
Right. Exactly. Okay. So that's convergence and divergence. Now, let's see here. Is there anything else that you need to talk about? Well, your book has a couple of theorems that I'd like to highlight concerning convergence and divergence. And the first theorem that I want to highlight, these are both in your book. They are theorems 2 and 3 in section 8.1. Are the sandwich theorem and the absolute value theorem? Namely, that if Bn is trapped in between An and Cn, and An and Cn both go to L, what's the obvious conclusion?
Oh,
And a very commonly used implication of this is the absolute value theorem.
Convergent network.
Which is that if the absolute value of A sub n goes to 0, then A sub n must go to 0. And I'd like for you to observe how this is cleverly set up in order to appeal to the sandwich theorem. The proof of the absolute value theorem is this. A sub n is always sandwiched in between its own absolute value and the opposite of its own absolute value. Consider this inequality right here, which is kind of obvious, but very, very useful. And because both of these go to 0 by hypothesis, therefore we conclude that An goes to 0 also. A good example of this would be a sequence that is strange, like this. Suppose I have a sequence that goes something like -1, 1/2, 1/4, -1/8, 1/16, -1/32, ... Notice that the negative signs here follow a random pattern. I can't tell what's going on with that pattern. But if I strip away the negative signs by use of absolute value, then I get a very well-behaved sequence. How would I write that sequence in closed form? Yep, we've got a good geometric sequence right here. And it's pretty clear that A sub n is going to go to 0 because the absolute value of A sub n goes to 0. So this is a very typical use, a common technique for dealing with this. Where we're headed tomorrow is this. We're going to talk about a third way to express the form of a sequence in terms of recursion, and we're going to tie that into the proof technique of induction that we have used sometimes this year. You guys are going to get good at induction by the end of this week. See you tomorrow.